Sometimes in a Bayesian model you have a number of parameters and it's hard to understand how you should choose the priors for the parameters. So in this video, when we're going to create a Bayesian model, we're going to look at what's called the prior predictive. So basically it means we're going to sample only from our priors, so not from the posterior, but just from the priors, and we're going to check whether that gives us results that are somehow consistent with what we know about the data. So I'm going to illustrate that in a second. And the idea is then that you're going to play around with your priors in such a way that the prior predictions look somehow plausible. Yeah, so let's create our model for the COVID data, for the number of cases. So we're going to have a time variable t, and of course we don't want dates here, we simply want to have it run from 0 and then long enough that we can cover the whole data frame. And we're going to model log cases, which is going to be equal to numpy log of data frame cases. So now we're going to specify our model with PM model as exponential model. And then we're going to specify our priors in a second. Let's first look at the model that we want to have. So the model that we have in mind is that the number of cases is equal to A times 1 plus B to the power t. Yeah, so we're going to have an exponential model basically. So now we have to specify the prior for A. Now there's not an awful lot that we know about A, so except we know that it's going to be positive. Yeah, because A determines the sign of Y, and Y is the number of cases. So we're pretty sure that A has to be positive. So let's say it's half normal with parameter 10. Then B, which is basically the rate of change, but this is of course we have daily data, so this is the rate of change from day to day. That in the way we formulate it, that can, of course can be both positive and negative. Of course, over the range where we have exponential growth, we expect B to be positive. Yeah, this 1 plus B is of course closely related to the R measure that is often mentioned in the news. If 1 plus B is bigger than 1, then we're growing. If B is negative, so 1 plus B is smaller than 1, we're in the range where the epidemic is dying out. Yeah, so in principle this can be normally distributed because B can turn negative. It's not very likely over the range of data that we have, but in principle it's not impossible. So let's say we have a mu of 0.1, yeah, which is small, but this is day on day, so this can't be too big either. And let's say we have a sigma of around 0.1 as well. Yeah, so we're allowing for negative values of B, but not values of B that become smaller than -1, yeah, because that would again turn Y negative. So this is A and B, so then we get our specification of Y. Then of course we need to formulate a noise term, so let's say this is half normal, EPS, 1. And the thing that we're modeling is log cases, and we're going to assume that this is log normally distributed. I'll come back to that in a second. Log cases, mu is equal to pm. So I'm here using the log function from pymc3 itself. So that's in the math library. So that's log y, sigma equals to EPS, and observed is equal to log cases, as we defined above. Yeah, so here we say that our variable log cases is log normally distributed, which basically means that this has a peak at the relatively small values of the variable, which means that the noise around our prediction of mu is somehow smallish. Yeah, so feel free to try at home replacing this with a normal distribution. But basically you're going to see that your prediction intervals are going to be huge. Yeah, because we have a process that is exponential. So you have a normal distribution and you get sort of errors around 2 standard deviations away, which is pretty to be expected with a normal distribution, which is quite likely to happen. Then you get enormously big intervals. Yeah, so that's why we choose the log normal here, but run this code with the normal distribution here, and then you will see at the final picture where we check the fit of the model that your prediction intervals are going to be huge. Yeah, so the trick that we want to look at here is prior predictive is PM sample prior predictive, and let's say that we want to have 50 samples. Yeah, so the idea here is that it's sort of hard to determine the separate values of A and B in this exponential process, but we know something about the outcome, about the number of cases. We know something about Y. Yeah, so we've plotted the number of cases before in the previous video, so we know what these are. We know sort of the range that they have to be in, and we can check whether with the priors that we specify here, we're sort of covering that range. So let's run this, see whether we have any errors. No, seem to have run fine. So then we're going to plot our prior predictive for A, B in zip. I'm going to explain in a second what zip does exactly. So we have prior predictive for A, and we have prior predictive for our variable B. So now we know that Y is equal to A times, this is simply replicating our model, 1 plus B to the power T. So now we can plot this, PLT plot, T and Y. So we're going to make these black with an alpha equal to 0.4. And then we're going to specify, because this is exponential, so some of these really go off the chart, literally. So let's say this is 0, 500,000. So let's see what this gives us. So here we have our prior predictive. So each of these lines is an outcome from just our prior. So we have not confronted our model with the data yet. This is just based on the priors, and so a number of these really go up very fast. And some of these go up far more slowly, and some of them hardly come away at all. So if you look at our at the graph we plotted before, cases go up to around 300,000. Yeah, so we're sort of covering that outcome. Yeah, so some of our priors really go a lot faster, go up a lot faster, and then therefore get a lot higher. And some of them go a bit slower, and we get up here. So it seems that our priors are not unreasonable in the sense that when we simply predict directly from our priors, we're sort of in the right place in terms of what the outcome is going to be. So let me quickly show you actually what this zip command does. So for A, B in zip, and now we're going to give it two lists. So the first list is 1, 2, and 3, and the second list is 4, 5, and 6. And we're going to print A and B. Yeah, so basically what this zip command does is that it combines the first element of the first list with the first element of the second list. So I get 1, 4. The second element of the first list, second element of the second list, etc. 2, 5. Yeah, when it comes to generating our prior predictive, that's exactly what we want, because the first sample of prior predictive A corresponds to the same draw from the prior distribution as the first sample of prior predictive B. Yes, so indeed I want to have these combinations A and B, where I draw the first sample from this and the first sample from B. Similarly, I draw the second sample from the prior of A and the second sample from B, etc. Yeah, so that's what the zip command does. It allows me to very quickly combine these two lists in this particular manner. So now we can start to sample. So we say with exponential model, the trace is equal to PM sample, and let's give some samples for tuning. So let's say we have 2000 samples to tune. So this will take some seconds. It goes pretty fast, but it will take some time. So we get a warning that the acceptance probability is not exactly what it should be, but let's not worry about this here. So now that we have the trace, what we can do is with exponential model plot the trace of trace. Yeah, so here we have our trace plot. So remember, the thing that we're looking for is it should be sort of stationary, so it should not be trending upwards or downwards. It should be this condensed zigzagging, so not sort of a single line going here, but we should draw from the whole distribution pretty quickly one time after the other. So we need this condensed zigzagging. And the third element that we look for is we want to have that the different chains cover the same region. Yeah, so that's actually what you can see here, that indeed the different chains have a very similar density across the parameter values. Yeah, so in that sense we sort of trust the sampling process that we have from our posterior distribution. So then a second check we can do is we can look at the table of the summary for trace. Yeah, so this is the table that we get. Yeah, so one of the things we can look at here is whether the R hats are sort of all fairly close to 1, which seems to be the case. So here now I have my posterior values for A and B. So what we can do is now we can start predicting. So we say with exponential model, the posterior predictive equals PM sample from the posterior predictive of trace. So when that's done, we can start plotting our model. Oh, we get an error here. Ah, yeah, okay, because this is called differently. This is actually called log cases, and the same is true here. This is log cases. So let's see whether it runs now. Yeah, now it runs. So basically, what we do here is we have our observed data, which is the red line, and we have our purple prediction interval on each of the days that we have in our data. So we're able to capture almost the whole process, except for the last couple of days when actually the data goes up faster than what we're predicting. Yeah, so for instance, this could be the case because in the start it goes on rather in a flat way, so it might be hard to actually model this with an exponential distribution. Perhaps we should have started our model at day 75 or something, so I'll leave that for you to figure out. But on average, I would say that, you know, the fit is actually not so bad for our model. So what have we done here? So we look at the posterior predictions of log cases, because that's the thing that we're modeling. We're modeling the log of the cases. So to bring this back into cases, number of cases, we have to take the exponential. So we have this log cases, we take the exponential of that, and then we look at the percentiles at 2.5 and 97.5. So we have 95% of the mass of the distribution in between these 2 points. Yeah, so in between these 2 points is 95% of our predictions. So that's what we plot here using this fill between method. So for each t, I give it two values. So the 2.5% and the 97.5% of our percentiles. And then I plot log cases, and again I do that to the exponent, so we get actually the number of cases, not the log cases. And this is then basically the result that we get. Yeah, so the fit is not perfect, so this scope to tinker with the model, try to improve it, get a better fit here, especially on the last couple of days to capture that part better. But for a first try, I don't think it's actually such a bad model.